Okay, this is the third video on gravity and orbits. We're looking at energy here. Now, we know that gravity is a conservative force. If you remember, that means that the work that is done by gravity is independent of the path that you take and depends only on the endpoints, and that means there's an associated potential energy. But that potential energy is not, as I led you to believe earlier, mgh, because that is true only near Earth's surface. Instead, it's a much more complicated formula, and we want to find out what that formula is. So for the moment, let's imagine that we have a star, big M, and we want to find out what the potential energy is for a small mass, little m, located a distance r away from it. Now, in order to do this, we have to define a 0 point, and we'll define that 0 point to be at infinity. So in other words, what we're going to do to find the work is we're going to imagine that we start little m way out at infinity. And then we're going to bring it in to a distance r. And we'll find that as we move the small mass m closer and closer to the star, that the star does work on it. It makes it speed up because the force exerted by the star points in the same direction as the mass's displacement. And the change in potential energy is equal to the negative of the work done. And so we want to find out how much work is done. So work is equal to the integral of f dx, where in this case f is g big M little m over r squared. Dx is a differential quantity that points in the positive x direction. Or rather, dr is a differential quantity that points in the positive r direction. But since we're moving this particle inward, dx is equal to negative dr. And so we'll put a negative sign out front, and then a dr. And our limits of integration are that we're starting out at infinity, and we're ending up at a distance little r. And so what we've got is a negative sign first, and then the constants gm and little m. And then last of all, we have the integral of r to the minus 2, which becomes negative r to the minus 1 power, evaluated from infinity to r. So those negative signs cancel out, and we're left with g mm times 1 over little r minus 1 over infinity, but 1 over infinity is 0. And so the work done by the gravitational force is g big M little m over r. And we'll move on to the next page. And that means that delta U equals the final energy minus the initial energy, and that equals the negative of the work done. Now UF, that's the energy at point R, minus 0, because we defined energy to be 0 at infinity, equals the negative of that work done. And that is an equation that you need to memorize. Negative gmm over r is the energy. And the reason that that is always negative is because gravity is always attractive. Negative energy is associated with attractive forces, positive energy is associated with repulsive forces. So now let's see how that works. Well, Actually, let's look at something called escape speed. Now the idea is that the closer you are to a planet, the more negative your gravitational energy is. And that means that in order to escape from a planet, you need to add energy to your satellite or your spaceship. So the idea is, you've got this planet here, it has mass capital M, radius r, and you want to get your spaceship to infinity but not beyond. So you start out right there on the surface of the Earth, and you end up at infinity with negligible velocity. So you start off with some very large velocity, launch yourself into space, and then when you'll go an infinite distance away from the Earth, but you won't be moving by the time you get there. So the initial energy is the potential energy associated with this, which is g big M, little m is the mass of the spaceship, divided by r, and that's negative, plus the kinetic energy. And the energy out here is equal to 0 because you're at infinity, so the potential is 0, and you're not moving, so the kinetic is 0. Conservation of energy says that negative gmm over big R equals 1/2 little mv squared. The mass of the spaceship doesn't actually matter here, which is interesting. And if we solve for v, which is the escape speed, you get, oh, that ends up being positive, I made an algebra mistake there, 2gm over r square root. Again, don't memorize that, but you do need to know how to derive it. The idea is that if you have a spaceship that starts off going faster than that, it will eventually get out of Earth's gravity well. And if it's not going that fast, it will go into orbit or fall back down to Earth, depending on how the mechanics work out. And we'll do energy in orbits in the next video.